Many thanks, Michal, for the warm introduction. Many thanks to the organizers who invited me. And thanks to all of you for being here. You look awfully tired. And you should be. This was an exhausting 3 days. But don't worry, OK? I know something about the human brain now. And one of the things that we know about the human brain is that our brain is thirsty for stories, OK? And that's what's coming to you. I'm going to tell you a story, OK? And I see many in the audience are very young, and that's fantastic. That's optimal for me, for what I want to do. And this story will sound to you like a story of an alien civilization, but it's really the story of your tribe, OK? And I really want you to understand this, OK? I want you to feel that this is the story of your tribe. And tell me if I succeeded, all right? So, great. OK. So, what's the outline? I'll tell you about the origins of our tribe. I'll tell you about the early years. And then I'll tell you about modern times. The modern times, they're the times you know, OK? So I'm not going to say much about them. I mean, I'll tell you. I have a very good friend who is a very distinguished historian of ancient Greece. And once I introduced him to my daughter, I said, hey, she's majoring in history. And she said, oh, really? What are you interested in? He says, I'm interested in post-colonial Africa. And then he said, oh, I see, you are interested in journalism. Okay, so the last part is journalism. Okay, so I have deepest respect for journalism and journalists, and I know that they have a tough job to do and a hard life and a very risky job, as we hear all the time. But that's not my inclination and talent and ambition. Okay, so I'm going to tell you about history. Okay, cool. And in fact, instead of modern, I'll tell you a little about postmodern computer science. Okay, so excellent. What are the origins? You knew that. Logic, of course, and this great lineage is part of our origins. And it gave us a lot of things. It gave us hierarchies, data organization, oracles, things that we all love and no longer work. It gave us proof complexity, model theoretic complexity, Fagin's theorem. Proof complexity, model theoretic complexity. Frankly, we believe they don't work, but they might. Okay, so they're worth our especially model theoretic, which has been abandoned for a decade. They gave us P versus MP, and of course, amazing names. I want to remember a few of the dots that I omitted here, and they should be remembered. That's somebody I knew and loved and admired. Left us early. This is my very good friend, logician at Stanford and computer scientist, Zohar Mana, and another very good friend that many of you also know, who Zohar and Oded left us 3 days apart. Okay, so last September. Okay, I'm not going to bring you down many more times with this one. Okay, the second sort of ancestral tribe is optimization game theory, and this this is another fantastic lineage, and what it gave us is. These people, for the first time, realized that polynomial and computation and exponential are different. Okay, so and felt it on their skin. Gave us polyhedral combinatorics, which we have generalized in amazing dimensions in our tribe, in TCS. They gave us linear convex programming and their mysteries, which motivated a lot of complexity. Gave us P equals MP and Edmonds, okay, so Edmonds was one of the people who and gave us amazing colleagues. The origins, what's number 3? That's a good guess, right? Not really. Okay, so this is important, but its influence came later. Okay, so that's I don't count this as our origin. Here is what linguistics is our origin, okay? Noam Chomsky, it gave us the Chomsky hierarchy of grammars, which TCS folks rushed to complement with automata, machines, and so some very, very, very insightful and compelling equivalences. Automata theory, language theory, compiler theory, all these things came, and PCP, P versus MP, I'll tell you why it also gave us P versus MP, and gave us Les Valiant, okay, who started in this field. Tremendous influence on CS. Much of the research agenda in the 60s in TCS was about this. If you look at Fox and Stock in the 1960s, it was about that. Helped us understand how to write compilers, which was the great engineering problem of the time, and trained us for the real problems to come. Okay, so this is the Chomsky hierarchy: regular, context-free, linear space, recursively enumerable. All right, I mean, so I guess that in looking at your faces, I guess half of you have not seen this picture before, okay? So let me show you a few things about this picture. You can ask an interesting question. Does non-determinism make a difference, okay? Strange question, but basically it's the question, right? And the answer is no with an asterisk for regular languages. No, but it blows up the number of states. Yes in context-free languages. We don't know in linear space, and no for recursively enumerable languages. Okay. And if you think about it, P versus MP is a modification of the orange block is a modification of the red block, right? I mean, no, it's just a different elongated version of the red block. Okay. In fact, I don't know how many of you are aware of that. I bet you many of the old-timers are not aware of that. But that's where P versus MP came from in a very real sense. Because Steve Cook, in 1969, he took push-down automata, okay, which basically the non-deterministic version accepts all context-free languages, right? And said, what if I give it log n additional storage, okay? Immediately, I get an exponential state space. Sorry, a polynomial state space. And then what? It turns out that the deterministic version is P, the non-deterministic version is NP. Many people saw that, including me, and said, wait a minute, they're different, right? But I mean, no, but the proof of inequality breaks down when you add the more than constant space. Okay, so that's and that was 2 years before his NP completeness proof. Okay, so that's remarkable, I think. All right, next comes anybody recognizes these computer scientists? These are the who. The who. Okay, and this is and that's because. Talking about my generation. Okay, so because this is about my generation. Okay, so this is my generation. Okay, and so these are people who got some of the people who got people who are not in this picture are my friends, or at least were my friends. Okay, these are some of the people who got their PhDs in the same decade as I did, let's see, what defined the transitions between prehistory and history? Okay, that's what I'm going to tell you. And 3 things, 4 things, I guess. Strassen's algorithm. We heard about it, the previous lecture, which in many ways belongs to this generation. I'll tell you why. Cook-Levin-Karp defined the new era. Edmonds-Karp reconciled optimization with our stuff, and cryptography later. Okay, so these are the defining the sort of the eigenvectors of this the top eigenvectors of this decade. All right, I mean, and of these 2 decades. And the spirit is as follows. Okay, I mean, so basically, what I want you to understand is that what you were, okay, it's very different from you. It's definitely different from the next generation, right? I mean, we were nerd Boy Scouts, okay? I was told that the word halutzim may help me, okay? So, so that, or perhaps may abshay habitzot, okay? Yeah. So, and of course, we had a lot of fun, inventing algorithms and proving complexity results and exploring complexity. So, and of course, all of us worked on P versus NP for forgettable semester. But the point is that we were back then. It was different. Okay, CS first of all was small. Okay, it was 1. Number 2, it was us, the mathematicians, and the rest were engineers. Okay, the other fields did not have theorists. Now they do. Okay, if you know these conferences, Popul, Podsi, Pods, and so on. Okay, these were theoreticians. These were our folks. Okay, we were doing this. I was Pods and Podsi. Okay, other people were Popul, and so we worked on compilers. We worked on OS synchronization and scheduling, software engineering, relational databases. When a new problem would come up, okay, I remember there was for a few years back in the 70s, there was the promise of the future was a technology called magnetic bubble memory. Anybody remembers that? Thanks. Okay, I thought so. Yes, right. Yeah. So I remember, one morning, talking with Giannakakis and looking at each other and said, "Shit, we have to work on this now, right?" I mean, also, because thank God it was forgotten before our first paper. Okay, but you have to understand the spirit, right? I mean, it was our responsibility. It was our mission. Okay, so when VLSI came up, okay, so every theoretician studied the book. Okay, so that defined the Lambda book. Okay, so parallel architectures, AI, security. So everything was our responsibility. Okay, so we were the universal theoreticians of all computer science. Okay, and we took it very seriously. Okay, we were nerds. All right. I mean, so okay, good. And of course, we were interested in complexity theory. I mean, we love this picture. Right. I mean, and I don't know how this picture became this picture. Right. I mean, so yeah. So and frankly, so as Michal told us. I bear a small part of the blame, okay? So I can explain, all right? I mean, so I think I'll give you a narrative that will make you forgive me, all right? I mean, so here is how we felt. In the early years, NP completeness was extremely important to us, okay? Because in some sense, it was the message that computer science had to give to the world, okay? So we were very proud that people in all walks of mathematics and applied mathematics and engineering and science knew what NP completeness was, and they were basically adjusting their research careers for, according to this concept that came from theoretical computer science. Okay, so this was an incredibly valuable piece of fact for us. Okay, and at some point, we knew that the problem was impossible, but could not prove it NP complete, okay? And there were reasons for that. So what do? We consider it our mission to discover a new variant of NP complete, NP completeness to apply there, okay? And this is how it started nicely, so, co-NP completeness, maybe NP space completeness, and then, of course, it got out of hand, okay? But I mean, the point is, it was not us, okay, who are to blame, right? I mean, it was basically our mission mentality and the real world, okay? This is what brought us the mess, all right? I mean, so all right, so that's in terms of a parenthesis of apologia, okay? Good. All right, and then came sort of the hardest nut, which was the complexity of approximation. Approximation algorithms and approximability, which basically they put on the map, were put on the map by David Johnson in 1974, we considered it our field's second most important message, okay? Because it was a rigorous computational remedy to NP-completeness, and also the study of its obstructions, okay? So that seemed to us a perfect, the perfect direction for the field to grow. And incidentally, sort of, I don't want to bring down the party, but we must realize this, okay, that in stark contrast with NP-completeness, 45 years later, after Johnson's paper, the message of approximation algorithms has yet to be received by the intended audience, okay, which is how do you call it, optimization people, okay? So they try everything except for worst case, for the best worst case algorithm that we have, okay? So, and this is something that we should make us think, okay? It's an interesting, it's a very interesting fact of history that ignoring it is not an option. It's not good. Good, excellent. So, and so we had to construct a class of approximation, all right? And that was different. What is this class? Every complexity class was a mode of computation. Basically, it's a set of machines. It's a class of, is a infinite set of polynomial bounded machines. And computation is fragile, okay? By fragile, I mean that you change, out of a Python code, you take out a comma, and it compiles to something completely different. Right? That fragility is sort of is a very familiar aspect of computation, and of course, approximation is delicate. Okay, you cannot afford that. Right? So what do? And there was 10 years of arguing in the quagmire, okay? So we have been arguing back and forth. Here is a picture of that, okay? You know this guy, right? That's Michalis Giannakakis. So back then, we looked very similar, okay? I would go to conferences, and people would come up to me and said, "I'm sorry I didn't send you that paper." I said, "I'm Papadimitriou." I said, "Oh, sorry." But we diverged. As you know, a year and a half ago, we reconverged, okay? So our offices are next to each other, okay? So that's okay. Then we remember Feynman's theorem, okay? And basically, basically, really, for 10 years, I would visit Bell Labs twice a year, and every time we would talk with Michalis and say, "Are we going to shoot again 2 days by working on approximation, thinking about approximation?" Say, "Okay, let's do that." And it got us nowhere until much later. The class MaxSMP is a class of NP optimization problems defined in first-order logic. So that's that have some inf approximation ratio. And the question is this inf 0 or not? Is MaxSMP the same as pitas? And charitably, the name would soon be improved to APX. MaxSMP is a terrible name. And I believe that Madhu tossed the name APX. And minimization, as usual, would require, so as somebody who comes from optimization, I have been teaching optimization, I could not convince my students that minimization is different, okay? Because in linear programming and you write the two the same way, okay? So in any event, what's the MaxSMP idea? Use logic as the front man. In other words, use logic as the facade, okay, as the syntactic, as the expressive language, and then introduce computation in a safely non-fragile mode. Close the class under what you call L reductions, okay? Soon after that, I was giving a talk about L reductions, and somebody from the audience said, why would you call them L reductions? Okay, L reductions basically were reductions, for those who don't remember, and I don't think anybody remembers, that preserve approximation. Okay, so we call them. We just the joke I cracked at the time is we gave them the worst name we could because we were hoping they would be called Papadimitriou Giannakakis reductions. Okay, Okay. And many of the approximation enigmas that we have been struggling against, the whole community has been struggling against, were complete for this class through randomized. Okay, here is an interesting. We had to use randomized reductions, and the reason is that we didn't have explicit constructions of expanders, right? I mean, we needed expanders, what is the most amazing thing about this paper is that it was accepted in 1988 stock, and the legend goes as follows. I mean, it's really a legend. I cannot vouch for it. That it was heading to an inevitable rejection, and then it was saved by Fagin, okay, who was, I believe, was on the committee, and who apparently didn't want to miss the citation. All right, I mean, the argument for its acceptance is, but it uses randomized reductions, okay, which was to us the only flaw of the paper, okay, right? So in any event, that's history. So after we did that, we thought we could rest on our laurels, right? That our mission was accomplished, okay? And basically, that's what we had been trained to think, okay? Here is why. Because in our trailblazing career through complexity, we have been leaving behind us classes, okay, that nobody would ever collapse, okay? So we said, well, this is the fate, okay? We more and more classes, and yeah, right. I mean, they're going to prove that it's MP, okay? Yeah. Who would expect that, okay? But it was, the time was ripe for further progress, and there was another intellectual stream, okay, that was rushing in the same direction, sort of, and basically pushed everything further. And by the way, the next generation has already arrived, okay? It's 1980. So as you notice, all of these people, again, all of these people have to do, we are cryptographers, right? I mean, so cryptography was the word of the day, okay? It was an amazing, so in 1976, we read the Diffie and Hellman, and we said, wow, okay, why did we read it? Because basically it was talking to us, right? I mean, it was said, we're in the dawn of a revolution in cryptography because today we have algorithms and we have complexity. And we read this and said, wow, okay? The dark side has noticed that we are here, okay? Yeah, okay? And then you have RSA, right? And then we have Rabin, Yao, Blum, others. So, TCS takes over cryptography. Okay, it became now our game, all right? And then, of course, later there is probabilistic encryption, and basically we redefine the field, okay, completely. Okay, so this is sort of amazing. So I consider it the Gardner of miracles of TCS, okay? When people, non-cryptographers, think about cryptography, okay? We have a smile on our face, okay? The smile over the decades became more puzzled, okay? But still we have a smile on our face, right? But confused, all right? It's also the enfant gâté and enfant terrible. Enfant gâté means beloved child and a little spoiled, okay? And enfant terrible means a child full of surprises, okay? Not all good, okay? And intellectual vanguard, okay? Because these people had to have more vivid imagination than us, okay? So they were really leading us. And this is very true. You'll see the rest of the story. And also our favorite narrative. What do I mean by that? I mean the following: that when an annoying systems colleague corners me, and you tell me, why should we hire another theoretician? Okay, and they say, tell me one thing the theory did. Well, I say, we are exploring the reaches of the universe. We are bullshit. Why should we hire another theoretician? Because bullshit. Why? I said cryptography. Oh, I see your point. Okay. Yeah. So this is favorite narrative, at least, or in one practical way. Okay. So and then sort of cryptographers got completely out of hand, okay, and started asking questions that sort of, that made us roll our eyes, okay? What is the proof really? We know what the proof is, okay? So, we always thought it's MP. And then, but they were more ambitious. They defined a class that was more open-ended. And we roll our dice and say, oh, we know it's MP. But then it started showing signs not being MP, okay? And then we started paying attention, right? And then suddenly, in 1990, IP takes over all of space, okay? Not only that, but MIP, which we didn't even know what it's about, okay, because it's not proofs, right? It's not mathematical proofs. Goes even further, okay? And suddenly, error correcting code starts playing a role. And more importantly, some clever folks start scaling IP and MIP back, okay, so down to stuff we cared more about. In very, very intriguing ways. The connection to approximability suddenly became very, very obvious, okay? Because the sole purpose of proofs is to create a gap between truth and falsity, and in approximability is a gap, right? So this starts becoming really relevant. And they looked for the correct path to scale back, and it turns out that the correct path to scale back were query bits and random bits, okay? And if random bits are logarithmic, then the state space becomes polynomial, okay? So, and the formula becomes polynomial, and things become very interesting. And this was first explored by Faye, Goldwasser, Lobas, Safra, and Szegedi. Streamlined in Aurora, Szegedi, and apparently, sort of, back then we knew what PCP was, and it was not mathematical, okay? It was chemical. It was called phencyclidine, and by the way, a PCP fest in California in the 1990s would not go down very well, okay? Okay, and of course, completed a few weeks later by Aurora, Lund, Motvani, and Szegedi, you're right, yeah. Sorry? Sorry?
I said this one I knew correctly even in my talk.
Oh, yeah, right. Okay, good, great. PCP was a huge deal, okay? So I'm telling you as an outsider, right? So everybody stopped what they were doing, and for a semester, and so they were admiring PCP. And it's a miracle in the house. So it's sort of an amazing thing. It caught the imagination of all computer scientists of the world. And then, of course, the next 10 years led to amazing improvements of newfound sophistication, and ushered in the modern era of TCS, and eventually, of course, to the unique games conjecture and the present celebration. All right. So, with this, I want you to remember Rajiv, okay? So who was one of the co-authors of the PCP paper, and left us early, 2009. Okay. And now I'm coming to the postmodern era, and because I don't want to be journalistic, I'm not going to tell you much, okay? I'll just tell you what marked the transition. Certainly PCP. The second was quantum computation, which made us realize that this is not the old field, okay? So, PCP, quantum computation, we're not in Kansas anymore, right? And of course, around the same time, the internet. And the internet came and changed everything, okay? I'll tell you a few things about the internet. That's the internet, okay? That's the internet in the early 1990s, okay? It promises a global system of abundant information, communication, democracy, publicity, equality, okay? So everybody is a global reader and a global publisher, okay? So, you don't need to go by the censors anymore, okay? So, it's sort of an amazing, it's education, interaction, entertainment, gossip, opportunity, okay? Everything. So it was a dream come true, okay? I'll tell you the following, that was the first time in my career when I told myself, I don't only want to work for this, but I feel I have a duty to work for this. You see what I'm saying? That I saw it as a political imperative, okay? I'm not going, many of you know, I'm a political person. I always wanted to change the world. But very soon in my life, I realized that I'm not good in politics. And the reason, I have a very simple reason, two reasons. One is I'm not very persuasive because when I'm very sure about something, okay, people don't believe me, okay? And number two, I'm easy to be persuaded, okay? So when somebody tells me something else, I say, oh, I see your point, okay? And that's not good for politicians, right? So I decided not to be a politician, but to be a good scientist and do good work and think correctly, vote correctly, and that's it, But when the internet came about, I said, wow, by doing computer science, and I can help the world be a better place, okay? And this is where I decided I should work on this, okay? Okay? 2 decades later. The internet now is a plantation, a vast plantation, where the cash crop is data, and where the whole world population is slaving. Okay? This is an amazing betrayal of a dream. Okay? And it's not going to stay there this way forever, right? Everybody's thinking, when is this going to change, all right? And very few people are thinking, how is it going to change, all right? And one idea is this, okay, that Internet 3.0 could be based on blockchain, okay? So why blockchain? And I know I'm now consciously hitting on one of the themes of the conference, right? And blockchain to me is the following, amazing idea, right? That somebody 10 years ago wrote a piece of code, okay, which has been basically a distributed computing system, which has been used and executed by tens of millions of people. And no bug was ever discovered. Excuse me, 0 bugs, except for one game theoretic potential bug. Okay, in a second that I'm writing a paper about. Okay? So, this is amazing. Compare with the rollout of Obamacare. Right? Like a system 1,000 times simpler that had millions of bugs. Okay? So this is sort of an incredible, if you think about it, if you think about it in terms of computation, okay? The internet is a different kind of computation. So Michal and I, and the people working in algorithm game theory know that what the internet is a machine where the input gates and the logical gates, they need to be incentivized, bribed, in order to work correctly. Okay? This is what the internet is. This thing is something much more advanced. This beast is a machine which wants to run, and because it wants to run and needs to run, it incentivizes you. Okay? It gives you money to run it. Okay? It's very interesting, okay? So, it's a big transformation of, I hope you get what I'm saying, right? I mean, so it's a huge transformation of the field, okay? It's a very new conception of algorithm. Of course, as we know, beasts die, okay? And this beast is not feeling well right now, okay? This particular beast. But this is not a beast, sort of, it's a family, it's a genus of beasts, all right? I mean, I'm sure that something good will come out of the Bitcoin story. In any event, the internet is, suddenly computer science realized that the computer is nothing. The computer is the gadget that brought us the internet, okay? And basically, the internet is what we are all studying now. CS became a natural science because the internet is something we didn't design. It's like a natural object, which complex object like the cell, like the brain, like the market, okay? That we have the universe. We have to approach it with the same humility that other sciences approach their own subjects. It's also a social science because the internet is about people. And if you don't understand the people, their objectives, their behavior, their cognition, you cannot understand the internet. So it completely transformed computer science. And the role of TCS became very, very outward looking. So, it's a lens on the sciences, okay? For economics and the internet, there is algorithmic game theory. And also, there are many, many other things, and I mentioned the things that I'm interested in. TCS and evolution, the TCS of deep learning, what Sanjeev is working on now, and TCS and the brain. And actually, that's what I'm going to spend the last few minutes of my time telling you about. So I had a precious few questions. I mean, if you want to bring out something in the middle, right now, I'm open to it. But now I'm going to tell you something about the brain, okay? So the last 4 years I've been working on this, okay? It have been the most exhilarating and interesting and challenging, also the slowest in terms of publishing years of my life. And I still work on more than 50% on other stuff, but this is this makes me wake up at night, okay? So that's and the real question is not how the brain works, but how the brain computes, okay? This is because, frankly, what is the lens, computation as a lens for the sciences, right? Computation as a lens of the sciences is essentially fantasizing that the scientific object you are studying, like the market or the cell, wants to compute something, okay? For the brain, it's very easy to imagine that the brain wants to compute something. You see what I'm saying? So it's sort of, it's par excellence the great sort of object of computer science as a lens. All right. So how does the brain compute? And it turns out that this brings us back to our roots. Okay. That, as I explained them, back to logic and language. There are people who are taking us to optimization. Okay, they say that basically what the brain does is optimize some kind of complicated function through gradient descent, but so don't pay attention to them. Okay, so it's all right. So so you see what I mean. This is the book. Okay, the book is called Kandel and Schwartz. It's a 3,000-page book. 5 years ago it was 2,000. And if you think about it, the title is Principles of Neural Science. And if you think about it, that cannot be right. Okay, that every edition basically the principles become more principles, right? I mean, when the Greeks decided to find what are the principles behind mathematics, in the end, old man Euclid came up with 4 lines, right? Not 4,000 pages, okay? So there is something wrong with this picture, right? That's what I'm saying. This is the man. His name is Richard Axel, Nobel Prize 2006. I almost said 1906. 1906 was the Nobel Prize of Ramon y Cajal. When you are young, you confuse years. You say, was it last year or the year before? Okay. When you are old, you confuse decades. Okay. I just confused centuries. What does this make me, right? Okay, so, all right. So, okay, so here is what Richard Axel is, to my mind, sort of, you know, the greatest working neuroscientist. And here is what he said 2 months ago in a Neuro magazine. We did not have a logic for the transformation of neural activity into thought and action. I view discerning this logic as the most important future direction of neuroscience. So I could stop my talk now and tell you that I have a pretty good idea of what the logic is, okay? You know, but I think I'll also give you some hints, okay? If you want. Okay? You want to? Okay. So I'll give you some hints. All right. Yeah. So this is work with these 3 people. Santos, you know. Wolfgang Maas, the old-timers might know. He was a computer scientist, but the last 25 years he has been a neuroscientist. And Mike Collins is an NLP person, so you know, a colleague at Columbia. Very distinguished NLP person. So, I'll give, you know, what you do in this business, you read experiments, and you hope that they are the right experiments and not the experiments that are going to come up in a week in the newspapers as sort of, you know, false or unverifiable or falsified. And so, you know, so you have to choose your experimenters, your experiments very, very carefully. But I mean, no, I totally trust this experiment. It's a beautiful experiment. I'll show it to you. So here is what this guy Peppel, he's David Peppel. He's a neuroscientist at NYU. Read to patients to whom he was recording by many technologies a tape that had a boring sequence of words, all of them in English, but also he did it in 5 other languages, single syllable words. Okay. For example, here is what, and very filtered to be extremely monotonous, okay? So can you imagine, so these poor people, they had to hear this for 10 minutes, okay? So basically, he said it at 4 hertz. 4 hertz is a very interesting frequency. 4 hertz is the frequency with which we communicate with the world, okay? Now I'm talking to you in 4 hertz. Your eyes make about 4 or 5 movements every second, okay? You know, in order to capture the scene. All right. So 4 hertz is extremely important. It's called the Theta rhythm. Okay. It's very, very important. So, and then he do a Fourier analysis. I'm trying to touch base with every talk today, right? You know, he did a Fourier analysis of the results of the you know, he had many dozens of patients that some of them intracranially, some of them by fMRI and so on, okay, but some of them by EEG. And he found that there was a huge peak at 4 hertz, which, of course, right? Then he did something clever. Can you guess? He did the same thing, except that every 4 words that made sense. Okay? Okay? Get it? So it's the same experiment, except now there are 4 sentences, and there are sentences that are a so a balanced binary syntax tree, right? Bad cats eat fish. New plan gave joy. Little boy kicks ball. Okay? And then he did the same thing, and what happened? There were 4 peaks. Okay? How do you explain this? Okay? He had to argue with 5 neuroscientist reviewers in order to publish his papers, and they all agreed that my interpretation is right, okay? Which that what it means is that what the brain does is this. Okay? I mean, no, it leaves me absolutely no doubt that what happens once every second is that a sentence is created, okay? What happens twice every second is that a phrase is created. Okay? What else? Think about it. So, it's a very compelling experiment. Okay. This is your left brain. This is where language happens. This is Broca's area. This is Wernicke's area. If you have aphasia, if you have a lesion here or a lesion here, then you cannot speak. If you have a lesion here, you understand all concepts, you understand all words, you cannot put together a sentence. Okay? They tell you that the truck hit the ball, and you think that the ball hit the truck. Okay? You cannot create syntax trees. You have a lesion here, and you don't know how to use words. Okay? You make sentences that make no sense. You don't understand the words. You don't understand the words that are told to you. Okay? So completely different forms of aphasia. What are assemblies? The mammalian brain represents memories by large and highly connected sets of neurons called assemblies. Okay, what is an assembly? An assembly is a set of 10,000 neurons, perhaps. Okay? Your mother is an assembly in your brain. Okay? Maybe it has many copies in many areas. Okay? And every time you think of your mother, one of these assemblies fires. Okay? So I am an assembly. Okay? So you know what the funny thing is? After my talk, you will not only have assemblies, but you are going to have an assemblies assembly. Think about that. But don't go this way, okay? Yeah. Okay. Okay. So, 70 years ago, Hebb, who is the founder of modern neuroscience, conjectured that that's how we represent memories. And they were suspected for 6 decades, and now they're verified beyond doubt. Okay, they exist. And they exist not only in our sensory cortex, which we knew for many years, but they exist in the rest of our cortex. Okay, and what I'm interested in is the rest of our cortex. I mean, frankly, I'm more interested in humans than most neuroscientists. Okay, and the reason is that the rest of our cortex that is not sensory grew from over primates and humans 10 times more than the sensory cortex. You see what I'm saying? So this is where intelligence resides. Okay? And it is called, the old-fashioned name for it is association cortex, which means cortex that is about thought and not related to any sensory input. And the point is, what do they do? What do they do in our association cortex? Okay, this is the big mystery. Okay, and here is the assembly hypothesis, which basically my hypothesis that assemblies are the data structure underlying our high mental function. In other words, there is a programming language, okay, which runs our brain, and this programming language, which to our credit we didn't call assembly language, okay. Has the basic data structure are these assemblies, these big sets of neurons, okay? And we believe that underlying our higher mental function, deduction, planning, language, storytelling, music.
So they're not disjoint, right?
Sorry?
They're not disjoint.
No, cannot be. Yeah. They're essentially random, except for this amazing thing that they're highly connected, okay? And the question is, in a GMP graph, how do you choose highly connected subsets, okay? That's not easy, okay? So, I've asked people whose day job is to do this, okay? So, to find graph algorithms for, and the brain does something more clever than what it came up with.
And if I look at the assembly for my mother, the assembly for my father, the intersection has to be?
Yes, it's coming next, okay? Yeah. I mean, there is of course random. There is birthday paradox. There is random intersection. I mean, you cannot.
Planted assembly.
Sorry? Yeah, they know how to plant assemblies in mice. So it's sort of amazing. Yeah, the plant assembly problem. Okay, so you see, we have, you won't believe this, but there is research proposal in the desk of NSF with a paragraph about this, okay, about this problem, okay? Yeah, so in any event, so what I'm saying is that what we have done, okay, everybody knew about assemblies, right? I mean, what we have done is we've come up with operations with assemblies. Project is something that we know happens. We knew from experiments, but basically means that an assembly creates a copy of it in another brain area, okay? It's like an assignment, except it's much stronger than an assignment. When you say X gets Y, X and Y go on to live an independent life. But here in the assemblies, they are forever locked together, okay? Associate, that's exactly, so, when, your father and your mother are associated. Association is more than random overlap, reflecting, for example, coincidence, sort of co-occurrence, correlation, affinity of some kind, and so on. Okay, so this is a very key operation, and we know that this happens. Okay, so if you see a picture of your father, of your uncle in front of the Eiffel Tower, okay, Eiffel Tower assembly and the angle assembly will come a little closer. Okay. Reciprocal project, which means that you project, but then the projection has a harness on the original assembly. Okay, can make the original assembly fire, which is a very important part. Pattern complete, which is the following: that if you remember, sort of, if you know that your uncle has just been to the Eiffel Tower, right? And then I show you a picture of the Eiffel Tower. Will your uncle complete or not? Okay. That's an incredibly, the pattern complete is an incredibly interesting mode of randomized computation. Okay? How by firing other assemblies you can make other assemblies fire. That's sort of, with some probability, some low probability. Okay? And this creates a very interesting form of computation. And merge. Merge is what happens in language. I believe that only we have it. Okay, so I'll tell you about it. Okay. Operations are observed in experiments, verified in simulations. So all these operations, first of all, we didn't make them up, except for merge, which basically verify the Purple experiment. We have a better grasp on existing experiments if we conjecture that they exist. And also, and proved, in other words, we can compile them down to simple neurons and synapses. We proved them in a yet realistic math model, and we verified in very realistic simulations. Okay, so in professional simulations of neurons. Okay, so that these are not sort of our fantasies, but it turns out that the computational system they define is Turing complete. Okay, which, I mean, if I want to tell you that this is how deduction happens, okay, you expect this from me, right? I mean, that at least be Turing complete. It turns out that it can do square root of n space, arbitrary square root of n's probabilistic computations of high probability, and where n is the size of every area. And finally, we have proposed brain architecture for syntax that is based on merge. How am I doing with time?
You have 5 minutes.
Okay.
However you need.
Okay. So what I only need 2 minutes to show you essentially the guts of our mathematical model, because I think that's what may be very interesting, most interesting to you. So I'm telling you that we have proved that these things happen. What do I mean by proof? So here is the mathematical model. That we assume a finite number of brain regions. It has to be an abstract model, right? We postulate that there is a finite number of brain regions. Without of generality, each contains n neurons. And k is the number of neurons in every assembly. Okay? We assume that both of them are constant, but sort of, it's not. It's a detail. Okay? Some pairs of areas are connected by a directed bipartite random graph. All areas are connected by recurrent GNP. Everybody understands what I'm talking about? Directed GNP. So it's a very complicated graph. All right? we know that this graph is not GMP, okay? That it has other, but it's eminently wise to prove things about GMP, okay? So, you know, and a lot of our arguments are improved, you know, so, you know, there is something called GMP++ that takes into account what we know about the synaptic connectivity in the brain, and our theorems become easier, okay, and stronger. So basically, you know, think of that every area has about 10 million cells. Every assembly is about the square root of it or a little more, and that P, the connection probability is 10 to the minus 3. Neurons fire in discrete steps, okay? Time is discrete, which is an assumption that is as it is convenient theoretically as it is indefensible, okay? Except that to say that more detailed simulations, more realistic simulations also verify our results. The way they are selected is by the following interesting. That's the basic operation. Okay. If you ask me what is sort of, you know, the machine language of this machine, it is the operation random projection and cap. Okay. You get it? Random projection and cap. In other words, if there is an assembly here in this area, okay, and you want to create an assembly in this area, what you do is you randomly project through this random graph, and then you take the cap. The cap means you take the k neurons that get the most input, okay? Out of the Bernoulli distribution, you take its cap. All right? And that's the only machine instruction in this language, okay? In this computer. And with this, you get the higher level language that I showed you. And finally, there is plasticity, that if there is an edge from I to j, I fires, and the next step j fires, then the weight of ij is multiplied by 1 plus beta. That's another thing that Hebb had predicted. And it turns out that it's true, even though it is a very simplified form of truth, and we know much more about plasticity. Neuroscientists are comfortable with using this. In any event, let me tell you a few more things about your brain, okay? So I told you about Broca's area and Wernicke's area, right? So here is something that you probably are not aware. Your left brain is anatomically different from your right brain, okay? If you are a right-handed person, then your left brain has much more white matter, has much more connectivity. These fibers become huge, okay? They grow by 60%. This is an asymmetry that is only found in humans, okay? Chimpanzees don't have it, okay? My theory is that this asymmetry is because that's the only way to implement merge. Of all our operations, merge is the most demanding, okay? It's the hardest to prove, and sort of, you know, it needs more assumptions to prove. It's the hardest to simulate. It needs the cooperation of between 5 brain areas, okay? I suspect that only humans had the real estate to create this, okay? And that this is reflected in these fibers here. This is called arcuatum fasciculum, and it's sort of, you know, a huge white area in our left brain. If you are left-handed and a woman, then the same happens in your right. If you are left-handed and a man, all bets are off. Okay, so you know there seems to be mixed data. Okay, but okay, so look at this picture, right? This is where we know this is where knowledge, like lexicon, resides. We know this is where Wernicke's area, where the leaves of the tree reside. This is Broca's area, where the internal nodes of the tree reside. Okay. Okay, and with this, I'm concluding my talk. I'll give you how I think sentences are produced. Okay, And I'm saying produced and not parsed. I mean, I have a hard time talking to my colleagues about that, okay? Because NLP people are obsessed with parsing. For me, parsing is sort of, a sort of rather boring reverse engineering problem. The miracle is how we say boy kicks ball, okay? How we see a picture, we see a fact, and we translate it into words, translate it into a tree. Okay, that's the miracle. Okay, and that's what I want to explain. And basically, here is what I think, how I think happens. We search, we see something, and we say, girl, kid, adult, no, boy. Okay, sorry. We first, the verb is the king of the sentence, right? I mean, so we first come, basically, what's a fact? A fact is that somebody or something does or is something, okay? So that's what a fact is. And the verb is the central part. So basically, what is this? It's a kicking, right? Kicking action. So basically, we find kick, and we project it in the verb area of the Wernicke's area. And we know that there are three different areas, one for object, one for subject, one for verb. And then who? Girl, boy, boy. Okay, we project there. Then toy, ball, ball. Okay, and we project there. Then we get a ride with the machine that does join, okay, and takes us to the upper area of the Broca's area. And this is called what is called verb phrase, right? This is a phrase has been formed. And then an inner node of the tree, okay? Inner nodes of the tree reside in Broca's area. And then the full sentence is formed. Okay, I have to, I'm finishing now. I have to tell you this. This does not explain how language is done, okay? What language is much more complicated than this, okay? Incidentally, what will happen now is that from S, we are going to go down the tree. So that's why these arrows have to be both two ways. They have to be reciprocal, okay? And then we'll eventually arrive here. And as a child, we have learned which order to do that because we were taught either to speak English or Japanese. So they have completely different, or Hebrew, that have completely different rules for that. And then from here, we are going to access some methods for articulating, for speaking, okay? But what I want to warn you is that I have not told you how language is done. Language is incredibly much more complicated than what I told you, okay? What I told you is that assemblies have the power, to implement the mechanics, the plumbing of language, okay? The very primitive and boring part of language, okay? Which, however, is very demanding, okay? All right. So, in conclusion, okay, so, assemblies and their operations may be one productive path of thinking about computation in the brain. Could be the seat of Axel's logic, what Axel is looking for. Syntactic structure of language can be explained through them. And future work. How do we learn? How can we make assemblies learn? Okay, especially predictive learning. We know we can make assemblies can learn hyperplanes. Okay, can do Winnow and learn hyperplanes. The question is, can they do the more interesting kind of learnings that the mind means? Okay, so when neuroscientists see a memory, something that stores something, they say, okay, what is it predicting? Because there is no thing about it. Okay, I told you history, right? According to neuroscientists, there is no other reason to remember anything except to predict the future. Okay. So the question is, how can assemblies predict the future? How can they do the kind of predictive learning that we know can be done by deep learning? And the next thing, experimental validation of the assembly operations, which we have grants pending to try to do. All right, so thank you very much. yeah, so, I mean, part of my history was PCP. I mean, so, right, yeah, so,
Yeah, this is probably the suggestion some alternative models for deep learning for neural nets. I mean, because you said,
yeah.
forget about this.
Yeah. So, frankly, I mean, in order to get grants these days for studying the brain, you have to have a section that says that, okay, this I think is very promising, so, you know, and I have held my nose and written chapters like that, okay, you know, that maybe assemblies could be okay. I think that a computer to simulate assemblies would be sort of, you know, an incredibly stupid idea, okay, you know, so, you know, I mean, the brain was cornered into doing this very reluctantly because of 3 billion years of evolution, okay, sort of, you know, it was cornered in this sort of, you know, very bad situation where he had to use assembly, okay, and I don't think it's, you know, but there is a lot of what we are saying you know. So if you look at the literature, especially you read the papers written by the founders, like so you know, Jan LeCun and Benji and so on. So you know, they and Geoff Hinton, they have a chip on their shoulder, right? I mean, no. They try to say, well, and then we can make our deep nets neurorealistic, okay, biologically plausible. And they are never convincing, okay? But I think that with these ideas, I can create deep networks that learn not as well as the, so you know, not the same performance, not 99.8%, but maybe 97%, okay? That are really neurorealistic, okay? So you know that by studying the brain, you can see that deep networks are not completely incompatible with what the brain can do.
Did you say what merge was?
Merge is two assemblies creating another assembly in a third area, so that this assembly is fires when both of them fire, and then if it fires, it can fire them up, both of them, and in any order it wants.
Would you say that there is kinetic assembly similar to Volt vector, like Volt vector, corresponding to the same?
Yeah, that's yeah, excellent question. I mean, so after I gave the talk about this, Sanjeev came up to me and said, "Now I know what you are doing. I mean, you are explaining us how WordVec is created." I said, "No, I'm not doing this. Okay, you are giving us a new method for creating WordVec. No, okay, that's not. But it's remarkably similar. Okay, so so it's similar. So I don't think that assemblies will perform the same way WordVec. Yeah, but it's the same idea. It's essentially the same idea. Basically, here it's 0, 1. Okay, so it's a subset. So but it's essentially the same idea. And there is also it's a network, right? So there are synaptic weights that are changing and connecting these, or which didn't exist in WordVec, right? I mean, but yes, it's very, very parallel.
You said that we first see the key, but actually we only see the bond and the child, right?
Yeah.
And then
Right.
we realize that there is a key.
Exactly. Yeah. So basically, what I think is that sort of this is deep waters. Okay. So and linguists have been thinking about that for a long time, right? I mean, but there is consensus that the verb is the king. Okay. So the verb comes first, and there is and then I'm trying to think, you see something. I mean, if you see a kid, you are not interested, okay? I mean, if you see a ball, you are not interested. What makes you want to record this fact is that this kid is going to kick the ball, okay? And then the kick becomes sort of, that's how I see it. Okay? I mean, is sentences, like sort of, John is clever, so it's different. Okay, so there are different kind of thing, but attribution. But This is, yeah. I think the same circuits work.
Going to another area of your talk, do you have anything about the slavery you talked about on the internet?
Yeah, certainly. I was thinking that everybody would nod, but not many people nodded. Okay, you know. So I think that that the current situation, where individuals are lured by clever code to give up their birthright in order for the privilege to use a search engine or a stupid network, is completely exploitative, you know, and completely against sort of the community that brought us the internet. Okay, so these people are exploiting. So, you know, I'm talking about Google, I'm talking about Facebook. Okay, I'm talking about all of them. Okay, they are exploiting basically, what is it? It's the new firm. Okay, a firm. Okay, what is a firm? Right? I mean, what are companies? Okay, there are like tens of books about that. Okay, you know, there are 4 generations of the theory of the firm. Okay, the new theory of the firm is that the firm is a company that creates products whose purpose is to become parasites on people, live with them, and communicate data about their lives back to the headquarters. Okay, so that the headquarters can turn around and sell this data, or in the case of Amazon, use them directly. Okay, and I think that this is an abomination that is not going to last for long. Okay, sort of, you know, I think that abominations, you know, sort of, you know, you put anything, any name you want there, don't last for long. Okay, you know, so people wake up. And one of the hopes in the future is that a new, more public, public way of building the internet will happen.